So we saw in the previous video that R1 and R4 managed to establish an Ospf adjacency, which is cool and everything, but how was that actually achieved? To understand how Ospf devices achieve and maintain adjacencies, we need to understand something about Ospf packet types and Ospf states. We will set our router IDs back to 1.1.1.1 for R1 and 4.4.4 for R4, and we can see that we have 5 different packet types and 7 different Ospf states. As soon as VMX R1 is configured for Ospf, it will start sending the first of the packets, the hello packet, sent every 10 seconds out all of its Ospf configured interfaces to the multicast address of 224.0.0.5. This is used something like a keep alive to establish and maintain neighbor adjacencies. However, as R4 is not yet configured for Ospf, the device remains in the down state. When R4 is configured for Ospf, it is able to receive the hello packet and registers R1's RID in something called the neighbor table. This is when the routers go into the init state. R4 now knows R1's RID and address and no longer needs to communicate by multicast, so it sends its own hello containing R1's RID and its own RID to R1's unicast address. When R1 receives this hello and adds R4's RID to its own neighbor table, the devices can transition to the two-way state. After this, the routers have a debate about which device should be responsible for ensuring that their link state databases are synchronized. The routers send an empty version of our second Ospf packet type, the DBD, the database descriptor, and whichever router has the highest RID becomes the master. The other router is going to be the slave. This describes the X-start state. They both then send their link state databases and send recognition with our third Ospf packet type, the link state acknowledgement. When each device has a description of their neighbor's link state database, then the routers are at the exchange state. If the routers examine the link state database and realize that they are missing some information, then they can ask for the information with our fourth Ospf packet type, the link state request. The device will reply with our fifth Ospf packet type, the link state update, sending the missing information as a response to the link state request. Then Ospf will again send a link state acknowledgement after a link state update. This is known as the Ospf loading state. Finally, after all of this, the routers can synchronize their databases and transition into the full state. Ospf packet types and states. I'm actually expecting this to be the most technically advanced video so far because I'm looking to show you the Ospf packets and the Ospf state on the actual command line. So let's have a look at the topology that we're going to be using. We have R1 and VMX R4 connected by GE001 on both sides. And I have R1 and R4 open. Let's just show Ospf neighbors. There's no Ospf running at the moment, so on R1 I will go into the Ospf protocol stanza or hierarchy and I will set some trace options to see the packet types. Now trace options are the Juniper equivalent of debugs. So trace options, let's set the file that we're going to record the trace options to. We'll call it Ospf log. And which packets will we set flags for? Well, we know we're going to use the hello packet. I think the only one we actually won't be able to see is the link state request packet, because link state request packets are only sent if there's some missing information, and I don't think there's going to be any. Let's use the database descriptor. The other one is the, well, let's see what they've got. Oh, they've got a whole heap. What I'm looking for is the LSA ACK and the LSA update. I'm only going to do the trace options on R1. Now from here, what if I say edit area 0 and set interface GE001.0. Let's commit that and do the same on R4. And as soon as I do this, when I look into the trace options file, I'm expecting to see hello packets and LSA acknowledgements, LSA updates. And commit. Alright, now we're jumping back onto R1. If I say run show log of the OSPF log, and we're going to match for hellos first. Not X match, just match for hello packets. And here we see that there was a hello packet sent from us, the local router, and it was sent to the multicast address of 224.005, and we received a packet from 10.1.14.4 on the multicast. I would have actually expected that to be unicast. Maybe these are the unicast packets here, unicast, where it's sending us unicast hellos. So the hello packet works. Let's have a look at the next one, the database descriptor. DBD, I think it will be called. Yes, and we've received the database descriptor packets describing our databases. And let's also look for the, because OSPF is a reliable protocol, we're expecting to see link state acknowledgement packets. Let's have a look for just ACK. And we see the link state acknowledgement packets as well here. Received a link state acknowledgement from 10.1.14.4, and it also sent a link state acknowledgement. It also sent a link state acknowledgement to the unicast address of 10.1.14.4. And the last one that we're expecting to see is the link state update. Again, if I just put update. Yes, and again, we see the link state updates are sent. Initially, they're sent to the multicast address, and then we're getting them to the unicast address. So these are 4 of the 5 packet types, which is good. Let's now move on to OSPF states, which is going to be a lot more difficult, I would have thought. And the only reason I want to do that is because we see a lot of theory, but I want to actually see it on the command line. Now, the first state is the down state. And this means that no hello packets have been received from the neighbor. Also, we can see the down state if a manually configured neighbor is being removed from the configuration. Let me just jump onto this side actually. Edit interface GE001.0, and we change the interface. Okay, neighbor. Let's say neighbor is 10.1.14.4. Oh, edit. Okay. What can we do under the neighbor command? Nothing. All right. Let's just say up. Up. Should have said up to. All right. So set interface GE001.0. We're going to change the interface type to NBMA. They're actually incompatible, but it should work. Let's commit this. Run show OSPF neighbor. Yes. So we could see the first state, the state as being down. That's the first of the 7 OSPF states. Let me say rollback 1. The next state is the init state. And we see the init state when an OSPF router receives a hello packet, but it doesn't see its own router ID in the hello packet neighbor field. Basically, this is if one side is blocking hellos. Now, when I done my Google through and I saw that it said one side is blocking hellos, the best way I know to block a hello is through a firewall filter. And that's what we're going to try here. Set firewall filter. Just going to call it block on the physical interface. And for the firewall filter of block, the first term, we're going to term 1. We're going to use the destination address. Oh yeah, let's say term 1 from the destination address of 224 1.0.0.5. Then we're going to reject this. Term 1. Then reject. And we need to allow everything out. So term 2 will be then accept. But that's not all. We actually need to apply the firewall filter as well. And we're going to apply it incoming on R1. Edit interfaces GE001.0 for the family INET filter. Set input filter of block. Let's commit that. Run show OSPF neighbor. Oh, nothing. Alright, let's see on the other side. Run show OSPF neighbor. Yes, and here it is. We've got the init state. That's the second of the 7 OSPF states. I feel like it's a kung fu movie. You have defeated 2 of the masters. You may have defeated me, but you'll never defeat the Grandmaster. So we've got down, we've got init. Now we're looking for, what's next? The two-way state. So again on R1, roll back 1 and commit that. We should see the OSPF states come back up. Run show OSPF neighbor. No, it's down. And maybe that's because rollback 1 was not enough. Edit protocols OSPF area 0. Let's show that. Ah, yeah, we still got that spurious command. So let's just delete this. Delete everything, yeah. And then I'm going to set the interface as GE001.0. Yep. Let's commit that. Everything's back to the way it should be. Now, the reason this is saying 10.10.10.10 is because it must be manually configured under the routing options here. Top edit routing options. Show, which it is. Let's change that. Set router ID as 4.4.4.4. Commit. Brilliant, it's changed. Right, the next one we want to attack is the two-way state. The documentation says, the two-way state indicates that the local router has received a hello packet with its own router ID in the neighbor field. OSPF devices will be in the two-way state if the neighbor is neither a DR nor a BDR. Now, the only way I know how to make routers not take part in the DR-BDR election process is if we make their priorities 0. So let's try that. Set interface GE001.0 priority 0. Let's see if that works. We have to do the same on the other side as well, actually. Top edit protocols OSPF 0. Commit. Look at this, that's amazing. So we now see that the state is in the two-way state. 3 down, 4 to go. We've done the down, we've done the init, we've done the two-way state. Roll back 1 and commit to make sure they go back to full. Which they do. So the next one is the X-start state. In the X-start state, the local router and its neighbor establish which router is in charge of the database synchronization process. The most common reason for this problem is a mismatch in the maximum transmission unit, which is the MTU settings. That should be pretty straightforward. I'll just jump onto R1, top edit interface GE001.0. Maybe it's on the family INET, I'm hoping. Set MTU. Is that there? Yes, it is. I'm going to change it to 1200. Now, the reason I'm changing it for 1200, if I say show interface GE, run show interface GE001, we can see that the physical interface MTU is 1514 and the logical interface is 1500. It will be the same on the other side. So now I've set it as 1200. There should be an MTU mismatch. Run show Ospf neighbor, and we see the X start state. 4 down, 3 to go. Now the next two are the most difficult ones, I think, to actually see, but we're going to try our best. So the next one is the exchange state. The local router and its neighbor exchange database description packets that describe their local databases. What we're going to try to do is get the router to re-exchange database description packets by adding an additional address. Right, sorry for the random transition. My computer decided to flip out. So as I was saying, we need to add an additional address. So under the interface GE001.0 on R4, we will say set address. And we're going to choose the address of 172.16.10.4/24. And let's just check under this to make sure. So what we will do, we will now check under the Ospf protocol to make sure that this interface has been advertised, which it has. Now we can see that when we do the show under the GE00 unit 0, both addresses are there. So if we commit that, then that will mean that both addresses are advertised into Ospf, and we need to do the same obviously on R1. So jumping on R1, we do a show protocols Ospf to make sure the interface is not advertised. So we only have one IP address advertised under GE001.0. So let's go into the edit interfaces and add the additional address. Set address 172.16.10.1/24. And we also need to advertise this interface in Ospf. Edit protocols Ospf area 0. Set interface GE0/0/1.0. And let's commit that. Now let's do a run Ospf neighbor, and we can see the loading state here. Excellent. We're hoping that the top one goes into the exchange state, but we've seen one of them, which is excellent. Oh no, it transitioned into full. That's not what I was hoping for. I was hoping that we would see the exchange state. But scrolling back up, we could see that the loading state is visible. Let's just try to have one more try and see if we could get that exchange state to show. So I'm jumping on R4. I'm going to delete the additional IP address that we added. So delete address 172.16.10.4/24. Let's commit that. And let's do a run show Ospf neighbors on R1. And we can see that the dead timer is running now, and it's on 22. Now it's on 17. Now it's on 12. Let's just clear the Ospf process actually. Run clear Ospf neighbor 172.16.10. 4. We can see that that neighbor is no longer there. Now we're going to add that address again and see if we could get it to change into the... Okay, rollback 1, that address, run show Ospf neighbor, and it transitions straight away into the full state. So it looks like the Kung Fu master was correct. We managed to see 4 Ospf packets and 6 Ospf states. That's it for this video. We'll see you in the next one.